Ever wonder why some AI systems sound too sure of themselves? Like when a chatbot gives a detailed answer to a question it's never encountered before. That's the problem this research is solving, teaching machines to recognize when they're out of their depth. At the core of this work are Gaussian processes, a type of machine learning model that doesn't just predict outcomes, it quantifies uncertainty. Think of it like a weather forecast that doesn't just say rain tomorrow, but also adds, there's a 70% chance of downpours, but we're still missing some data. That's the power of uncertainty-aware AI. But here's the catch. Traditional Gaussian processes are like super smart but slow detectives. They work great for small datasets, but when you throw millions of data points at them, they hit a wall. This research cracks that problem by combining two clever tricks: iterative methods and pathwise conditioning. Let's break it down. Iterative methods are like solving a maze by taking small steps and adjusting your path as you go. Instead of crunching all the data at once, the algorithm gradually refines its answer, super fast for huge datasets. Pathwise conditioning. Imagine using a map to navigate without retracing your steps. It helps the model adapt more efficiently, avoiding redundant calculations. The real magic. This approach turns complex math into something modern computers love: matrix multiplication. Yep, the same math that powers your phone's camera or streaming recommendations. This shift slashes memory use and lets Gaussian processes handle datasets with up to 5 million examples, like analyzing climate patterns or predicting how drugs interact with the body. The results: state-of-the-art performance on tasks from weather modeling to drug discovery, with speed-ups up to 72 times faster than older methods. But the real win: a framework that's not just faster, but smarter about uncertainty. Now, let's dive deeper into the math that makes this possible. Imagine you're in a kitchen, trying to figure out which ingredients make a recipe special. You'd want to isolate the key players, right? Well, in math, we do something similar with data. We use basis functions. Think of them as the building blocks of any dataset. They're like the essential spices in a recipe, each contributing something unique. And here's the kicker: these functions are linearly independent. That means none of them overlap or waste space. Each one adds its own flavor, no repeats. Here's where it gets wild. The proof shows that if your original spotlight wasn't the best, you could somehow light up more of the room. But that's impossible. The math says otherwise. So the only conclusion is that your original function was the optimal choice. This isn't just about lights, it's about eigenvalues, which act like the strength of these patterns. The biggest eigenvalues correspond to the basis functions that spread out the most across the data, like the most powerful lights illuminating the room's corners. And here's the really cool part. When these basis functions behave smoothly, like a spotlight that fades gently away from the data, they mirror a technique called kernel principal component analysis. It's like taking a chaotic, messy room and mapping it into a cleaner, simpler space where hidden patterns pop out. This is the math behind tools you use every day, from facial recognition to medical diagnostics. So what's the takeaway? This isn't just abstract theory. It's a mathematical guarantee that the most important patterns in data are the ones that spread out as much as possible, bound by the rules of their space. Next time you see an AI making a smart guess, remember, it's not magic. It's math, elegant, powerful, and quietly shaping the world around you. Thanks for watching. If you want to dive deeper into how AI handles uncertainty, hit that subscribe button. See you in the next video.